And the recording has begun. All right. Today is effectively our last day of new material, our last day of true traditional content to be taught in Chem 1A. This basically means you're at the end. Next Monday, of course, is a general review of the class. What I will do is I will come with your exams from this semester, and I'll try to spend as much of my time on Monday going through all of the exams. We'll probably skip through some smaller, easier questions just to accommodate for time. But next Monday's class is a review of the entire class as a whole, and that's through reviewing your individual exams. So if you'd like to carry your actual exams, or if you'd like to print new versions so you can follow along, that's fine with me. But Monday's class is basically a review via the exams you actually took this semester. All right. Now, the last 2 days, we've covered a couple of new topics. We've covered valence bond theory, hybridization, and of course, we've covered a little bit of inter and intramolecular forces. Before we jump into our last topic, we wanted to get some time practicing some questions on these two topics. To be clear, this particular problem set is not going to be collected for extra credit. Recall that for your final, the extra credit is that study guide opportunity, right? So this is just basically a practice worksheet of questions. We're going to go through some together. I probably won't assign any because we have another topic to get through. But for the most part, think of this as good practice for what kind of questions you can expect on your actual exam, on your actual final. Speaking of the final, I'll most likely have a draft by next week, so I'll be able to speak a little bit more about what exactly your final is going to look like. Before I begin, do we have any questions? Yeah, what's up?
Monday, we're going over the exams. Isn't that presentations?
Wednesday.
Wednesday's presentation.
Wednesday, December 3rd, the last day of classes, that entire day is presentations. Monday, the lecture is the review, and we have one more wet lab on Monday. Okay, so the people thought that presentation started on Monday. Okay. Okay, so because we do have another topic to get through, we're not going to have time to go over every single question, but I did want to talk about some of the big picture stuff. Let's first start with problem 1, aka polarity. The question says, draw appropriate arrows indicating the direction of polarity for the following molecules. If the molecule is believed to be nonpolar, then you simply write nonpolar. Now, let's remind ourselves of exactly what polarity is and what we're looking for. Polarity can be described as an uneven sharing of electrons. The idea is that some atoms love love electrons more than others, and as a result, they'll pull some of that electron density towards it. Now, one of the key factors behind understanding polarity is no longer thinking of electrons as discrete particles, but rather as clouds like you would see in the sky. So when we think of the more traditional shape of a cloud, it's easy to understand how a cloud isn't symmetrical. In other words, we could have a situation where the cloud on one side is larger than the other. Basically, it's an asymmetric cloud, where the size of the cloud, of course, represents the density of the electrons. One of the key things that we're looking for here when deciding uneven sharing of electrons is understanding which atom loves electrons more. Now, to answer the question of which atom loves electrons more, we think about ideal charges and noble gases. Recall that pretty much when it comes to adding or removing electrons, every atom wants to resemble noble gases. We think of, for example, that group 1 has a +1 charge, which means that it is, of course, likely to lose. Eventually, we get to, for example, group 15 that has a -3 charge. 16 is -2. I'm going to write this on another page so I have some space. Don't worry. So it's not just being blocked. Great. all the way to group 17, which is -1. And of course, group 18, which is our noble gases, of course, has a charge of 0. 2, 13, +2, +3, where that bit in the middle is, of course, our transition metals. When we think about the ideal charges of various groups, the idea of which atom loves electrons more becomes very apparent. In fact, it should be clear from the ideal charges that on the far left, groups 1, 2, and 13, all for the most part hate electrons. Why can we say that they hate electrons? Because they lose electrons. So they're okay with giving up electrons because they're not that fond of it. On the right-hand side, on the other hand, groups 15 to 18, you can absolutely say that they love electrons because they, of course, gain electrons. And of course, it makes sense why they would love electrons. Group 17, for example, only needs one electron, just one, to look like a noble gas. So it's probably going to be the first one that picks up an electron if it can help it. Group 16, on the other hand, although it does love electrons, it needs a total of 2. That's 2 separate processes. So although more tedious, it's the same result is achieved. Groups 15, 16, and 17 love electrons. The question, of course, is where does that borderline come from? I've purposely not included group 14. Remember that we said that group 14 is smack dab in the middle between the two noble gases. I was the one to go ahead and tell you group 14 will traditionally always be +4. So when we talk about loving electrons, we think about it from left to right. As they love electrons from left to right more and more. In other words, group 17 loves electrons the most. It only needs the one. Group 1, comparatively, you can say it hates electrons. In fact, it only needs to lose the one electron to look like a noble gas. So reminding ourselves of these ideal charges and the relationship to noble gases helps understand which atom loves electrons more. Couple of questions here. We're going to start with the first one. We're going to start with HCl. Think about where they are on the periodic table. We unfortunately don't have one up in the classroom. If you have your own copy, that would be great. Hydrogen is in group 1. Chlorine is in group 17. That is, of course, what tells us chlorine really, really loves electrons. So if we were to draw a cloud representing this uneven sharing, it would probably look something like this, where the most of the electron cloud is on the side of the chlorine. Again, this comes from that uneven sharing of electron density. As a result of this cloud, we can then say that the hydrogen is slightly positive and the chlorine is slightly negative. The symbols that I've just drawn is the Greek letter, the lowercase letter for D. You may, if you've ever taken a calculus class, you've probably seen this when you're done derivatives. But it simply means slightly in chemistry. So you read this as slightly positive and slightly negative. The idea here is they are not formally positive or negative. However, due to that uneven sharing of electron density, they are slightly positive and slightly negative. By doing this analysis, we're able to say that the polarity of the bond is such that it is in the direction of the chlorine, where the positive end is above the hydrogen. This arrow tells us beyond a reasonable doubt, it communicates to us beyond a reasonable doubt that the hydrogen is expected to be slightly positive and the chlorine is expected to be slightly negative. Do we have any questions on HCl? Trying the next one, FF. Of course, something we should immediately notice is that these are identical atoms. Identical atoms are predicted to love electrons identically. If they love electrons identically, that means there would be no uneven sharing of electrons. In other words, if I were to draw the cloud, to the best of my abilities, it would look like a symmetric cloud. This is what we describe as a nonpolar molecule. I would like to try HOH. Now, of course, the biggest thing that stands out to us about HOH, at least compared to the other questions, is that we have 3 atoms here. Okay, these are no longer 2 atoms in the molecule. These are 3 different atoms. So we want to understand, is there an overall net direction that's pulled? What exactly does that look like? Remember, to answer that, we simply look at how much these atoms love electrons. If I were to, for example, identify that, well, hydrogen is in group 1, oxygen is in group 16, I could potentially draw a cloud that looks like this, where again, the basic idea is the size of the cloud is asymmetric such that most of the electron density resides on the electron-loving atom. It is through this analysis we know, of course, that hydrogen is predicted to be slightly positive. Both hydrogens are predicted to be slightly positive. And the oxygen in the center is predicted to be slightly negative. In fact, I've heard some chemists go so far as to include another slightly symbol to make it clear from both directions there is some polarity going on. But you, of course, are not required to do that. This is what tells us we're going to actually have 2 polarity arrows, both pointing towards the oxygen, such that the oxygen is mostly negative. I'm going to talk about something else related to HOH specifically, but before I do that, does anyone have any questions on problem 1? Okay. The specific thing I wanted to mention about HOH is that solely based on how we've drawn it visually, these 2 arrows are, of course, predicted to be in opposite directions to one another. A very, very straightforward question to ask is, do they cancel each other out? Because presumably, they're pulling to the same strength in the same order because they're identical atoms. So in theory, shouldn't they cancel each other out? To that, I will say, think about the Lewis structure. And of course, the concomitant VSEPR geometry. If we were to construct the Lewis structure for H2O, we would end up with a situation where we would have 2 lone pairs on the central atom. When converted to the VSEPR geometry, it actually takes on a bent geometry such that the angle between the atoms is less than 109 degrees. Looking at it this way, the geometry, it should be clearer that although there is still that polarity, these angles or these arrows are no longer head-on colliding. In other words, they're not perfect opposites of one another. They would not cancel each other out. So it's important to reconcile the idea that although there is some cases where there will be a polar bond or a polar molecule, the geometry, the VSEPR geometry, ultimately dictates what it looks like. Compare this to something like CO2, which has the Lewis structure shown here. It's carbon in the middle with two double bonds, and each oxygen has two lone pairs. The central atom has no lone pairs either, according to the VSEPR geometry. This is linear. This is 180 degrees. If we were to look at the polarity of this molecule, remember the trends. We end up with a situation where you have to, again, the angles or arrows are in opposite directions of similar magnitudes. The molecule is linear as predicted by VSEPR geometry, so they are absolutely pulling in opposite directions. This is actually a case where the polar moments cancel each other out. This molecule, due to its linearity, is described as non-polar. Okay. I would like to do a couple questions from problem 3. Problem 3 just states bond types. Describe the bonding present in the bonds below. And of course, our options are sigma, sigma plus pi, or sigma plus 2 pi. Although these Greek letters are alarming at first, it's important to remember exactly what these relate to. A sigma bond is a single bond. A sigma plus pi is a double bond. And a sigma plus 2 pi is in fact a triple bond. The idea, of course, is that these letters, these Greek letters, sigma and pi, reflect the magnitude or the type of bond that exists between the two atoms. With that in mind, we're just being asked to describe the bonding present by use of one of those three answers. Starting with HH, we see here, of course, this is just a straightforward single bond. Single bond is just sigma. In the case of O2, zoom in so it's a little bit more obvious. This is the case where we have a double bond between the oxygen atoms. A double bond is defined as a sigma plus pi. And then finally, an N, well, that has a triple bond. We can tell that from the structure. We can tell that from the given drawing. This is, of course, a sigma plus 2 pi. Problem 4 bounces directly off of problem 3, so we'll just jump right into it. Problem 4 states, draw valence bond diagrams showing orbital overlap for the following molecules. Problem 3 told us the specific types and number of orbital overlap we've come to expect. We just need to know how to draw it. So reminding ourselves that a sigma can either be called head-to-head or end-to-end overlap. And a pi is side-by-side overlap. We can start with an easy one, which would just be HH, the top left corner of problem 4. Remember that the point of these diagrams is to very clearly indicate what orbitals are involved and how they specifically overlap. In the case of hydrogen, its valence shell is an s orbital, a sphere. So to show a single bond between the two hydrogens, remember that is of course a sigma bond, you simply have to draw the spheres such that they are very clearly overlapping with one another like so, just as you would a Venn diagram. I'm not particularly picky on how much that overlap is. For example, you could draw this. This is fine. But if it's very clearly not even touching, this would be incorrect. This just tells me they're close to one another. If you could at least get them touching in some way, shape, or form, that's incredibly clear overlap. Quick question, does this molecule have a polarity arrow? Or will it have a polarity arrow? No. It's the same atom, 2 hydrogens, so no uneven sharing. So I could potentially even ask you on the final, after drawing the valence bond diagram, draw the polarity arrow, but in this case, this is nonpolar. Let's try O2 over here on the right. O2 consists of a sigma plus pi bond. And hopefully we already know, of course, that the valence orbital in both oxygens is a p orbital. So we need to show the p orbitals sigma bonding as well as pi bonding. I like to start off with my oxygen in the center. And I say, okay. I know that first of all, it's going to have a sigma bond, which is, of course, the direct overlap of oxygen orbitals as such. I know, of course, that these lobes, there are lobes on opposite sides, so I don't forget to draw those in. Remember, I'm simply putting the oxygen smack dab in the center of where I would draw the normal p orbital. As shown, this is, of course, our sigma bond. I can very clearly see 2 p orbitals, one from each oxygen, head-on overlapping. Next up, we need our pi bond, which does not have end-to-end overlap, but rather side-to-side overlap that, although cannot be drawn quite accurately, we can make it clear just by use of these lines connecting the orbitals. This diagram, as drawn, clearly shows the sigma bond between the two p orbitals, as well as the pi bond between the two p orbitals. I like to call the, well, actually, no, I like this name, but I had a professor who called them flower petal diagrams because it looks like you're drawing flower petals. But recognize that it is limited by your drawing. I have seen a wide variety of these types of diagrams. Just as an example, if you didn't use any color, what I've actually seen in the past, this is how my professor taught on the board. No colored markers, and we were supposed to interpret what was going on from this that. Maybe you are just now if you see the color version to the right, but just imagine on a traditional whiteboard, it was a mess. So recognize that the clarity of the diagram is ultimately up to you. As long as you clearly show me the details I'm looking for, I'm not too picky on some other small stuff. Something I might see on, you might see on my own notes is I'll just make these outside lobes just a little bit smaller. Just because they're not actively overlapping, they're there, they're just not the priority. This to me is the same thing. We're going to do N2, but do we have any questions so far in valence bond diagrams? Yes, Joel.
Connecting top and bottom flower petals kind of imply a triple bond.
I can understand where that's coming from. To that, I will simply say, do you remember when we went back and did MO theory? We talked about something called bonding orbitals and anti-bonding orbitals. The two lines here are similarly meant to reflect that one of them is in phase with the other, one of them is not. If you recall back then, we did shading, but in this case, making those two connections makes it clear this is just overall a pi bond. I do get where you're coming from, though. It isn't an anti-bond, but I want you to think about it in the same way that they're opposites, meaning they're on opposite sides of a graph. So you just connect both to make, well, I could have also put a plus and a minus here to indicate these are in opposite arrows, opposite directions, opposite signs. You just need to show that they're both connected to one another. Traditionally, how that's shown is by shading, but you could have also done the plus and minus that I just wrote here. But that's not something I'm expecting for this topic. Any other questions before I try N2? Okay. N2, of course, is a sigma plus 2 pi bonds. And at this point, it should be no surprise that the p orbital is going to be the valence orbital. I mean, you guys remember I made a point of saying D and F are too complicated. You don't need to know to draw them. So any drawings I would ask you to do would be either SP, PP, SS, and all that stuff. So we have a couple of things going on here. We have a triple bond. It means we need to show a lot of stuff going on here. Let's try our best. First up, we have our sigma. I like to draw those lobes a little bit smaller simply because on the outside, just because they're not actively doing anything, they're still there, but I don't want to increase congestion. That, of course, shows our sigma bond. We then have our first pi bond. Connected as so. Just now I'm purposefully shading in to make it clear that they may be opposite signs, but they both will connect. This is, of course, our first pi bond, but we're not done yet. We still have to include our second pi bond, which will invoke the diagonal p orbital. And this here is our complete valence bond diagram for the triple bond of N2. That shows orbital overlap between, for lack of a better phrase, parallel orbitals. Of course, the verticals connect, the diagonals connect, and so do the horizontals. Do we have any questions on problem 4? Okay. About 12:30, so I'd love to get started on the new topic. If we have time at the end, I'll try to come back to one of the other problems on problem set 8. As a reminder, this problem set is not to be collected. There's no extra credit assigned. It's just, of course, you can be thought of as a regular practice worksheet for the 2 topics we did recently. Our final topic of Chem 1A is titled Nuclear Equations. Nuclear equations represent a new type of reaction It involves atoms broken down forming other atoms usually followed by a release of energy. This energy, to no one's surprise, this topic is nuclear equations, is referred to as nuclear energy. But what makes it nuclear? I mean, is there a traditional threshold that we can say this is an actual nuclear reaction, a nuclear equation that results in nuclear energy being released? I mean, in real life, we've seen examples all throughout history of nuclear energy, atomic bombs and all that. How do we describe or ascribe nuclear to some energy release? Well, traditionally, involves the breakdown or formation of radioactive atoms or their isotopes. Isotopes, there's a word we haven't seen in a long, long time. Reminding ourselves of exactly what an isotope is an element of the same kind with a different mass. I believe way back when we covered this in module 1, I gave you a couple examples. I gave you carbon 12 and carbon 13. Carbon 13 is very commonly used in radioactive dating. Carbon-13 is an isotope that is radioactive, and its concentration in an object, body, or person can be used to effectively date that object, body, or person to know how old it is exactly. This is one you most likely have encountered if you've ever been to a museum, of course. The other one that I mentioned was a more pop culture example. We talked about, if you recall, it was Spider-Man 2 with Tobey Maguire. We talked about the second one. Actually, no, I'm sorry, not the second. The third one, the third isotope, called tritium, which is, at least in the movie, believed to be an incredible source of energy. And now that makes a little bit more sense as an isotope, especially as a radioactive isotope. Its reactions, its breakdown results in a huge amount of energy, nuclear energy to be specific. There are 4 types of nuclear equations. I've shorthanded equations to E, Q, and S. Number 1 is alpha decay, represented by the Greek letter for alpha. Kind of looks like an incomplete bow tie. Loop. Alpha decay. Alpha decay reduces the atomic number by 2 and the mass number of an atom by 4. And what exactly does this mean? How does this relate to breakdown? In other words, what do these equations even look like? Well, let's take one of the most popular examples of a radioactive isotope, uranium. The atomic symbol is shown here, where the bottom number is, of course, the atomic number. And the top number is, of course, the mass number. How we would represent this as undergoing alpha decay is we would draw the arrow. Above the arrow, we include the alpha symbol, meaning this is going to be an alpha decay. We know that as a result of alpha decay, the atomic number goes down by 2. 92 minus 2 is 90. And the mass goes down by 4. 238 minus 4 is 234. But as we write this, maybe we remember that atomic number is probably the most unique identifier of an atom. Allow me to pull up a copy of the periodic table. Where is it? Where is it? Where is the periodic table? Where we know, of course, where we could find uranium. Uranium is number 92, but we didn't form atomic number 92, did we? We, in fact, formed a different number. We formed 90. This is a completely different atom. Looking at the periodic table, recognize that atom number 90 is thorium. TH. And I want you to understand at its core what's happening here. An atom is effectively being broken down and forming a completely different atom. This is not a traditional reaction where we've seen things combine or they displace one another, they combust. We are talking about a breakdown. It is this breakdown that results in a release of nuclear energy. And to show that a particle has been lost, we draw a product of mass number 4, atomic number 2, don't we know an atom with an atomic number of 2? Helium. So one common byproduct, or one very common byproduct, I should say, of alpha decay is a helium particle. Now, I would like to point something out. According to the periodic table, how we identified thorium, Th, was based off of the atomic number. We said that was our most unique identifier. It was our diagnostic number. That's how we knew, of course, it was thorium, as shown here. But if we look at the mass number on the periodic table, the mass of thorium is 232. We didn't form that mass number. Is this a problem? No. We formed an isotope of thorium. And this is one way isotopes are made in the world. Through these types of nuclear equations, through these types of decay, isotopes are formed or can be formed. That's alpha decay. Next up is beta decay, where again it has the symbol, the Greek letter for beta, which just looks like a cursive B, but it's a line just kind of hooks down like so. In the case of beta decay, the atomic number decreases by 1. However, the mass number is unchanged. An example of this is the beta decay of carbon-14. This is a new isotope of carbon that we're seeing. We've seen carbon-12 on the periodic table. We've talked about carbon-13. This is now carbon-14, so another isotope, another radioactive isotope. Its nuclear equation for beta decay is as follows. We put a beta symbol over the arrow to make it clear that's the decay. The atomic number, I apologize for this. I said it decreases. I should have said it increases. I apologize for that. It increases. I'm so sorry. The atomic number goes up by 1. In this case, it goes up to 7. Nothing happens to the mass number. Remains 14. So now the question is, what atom did we just form? Okay, well, we have to use our diagnostic tool. Remember, the one that tells us clearly what atom we formed is the atomic number. looking at our periodic table, number 7 is nitrogen. Just as before, beta decay results in the formation of a side product. That side product is represented by the beta symbol and looks like this. This beta symbol with the 0, -1 is merely to bookkeep the atomic number. Recognize that for the most part, the numbers should add up. 14 plus 0 is 14. 7 plus -1 is 6. So in the case of the beta particle, this -1 does not necessarily mean atomic number, but is rather used as a bookkeeping method. Because there can be no atom with a -1 atomic number. It's important to remember that when it comes to nuclear chemistry, nuclear equations as a whole, a lot of what we can do or study-wise is on theory. We can perform these reactions, we can carry out explosions, we can analyze historical explosions, but oftentimes it comes down to making sure that we've written everything down correctly, or rather kept track of everything correctly. The beta particle here serves the same purpose as the helium particle did up here. They're both bookkeeping, and they're meant to represent, hey, this was a radioactive reaction that released something. Next up, we have gamma decay. We use the Greek letter for gamma, which kind of looks like a Y with a loop on the right-hand side. In the case of gamma decay, there is actually no change in atomic number or mass. It traditionally involves the emission of light. In other words, gamma decay is what's been said to attribute, what we attribute the visuals of an explosion. Why in some cases, some nuclear explosions flash yellow or white or blue or green. Gamma decay doesn't necessarily result in energy being released, not in the way we would expect, but it releases light. An example of gamma decay. We have cobalt. We draw the gamma symbol over the arrow to make it clear this is gamma decay. There is no change in mass or atomic number. So it's the exact same element, cobalt, but it results in an emission of light, which is represented as a gamma particle 0, 0. Just as before, the gamma particle is, of course, used to bookkeep, make sure the numbers line up. And in this case, it's meant to represent that flash of light. Finally, we have electron capture. Not exactly a decay, it's more literally capturing in electrons. This is something most commonly used in the world of physics. They shoot electrons at radioactive nuclei to see what happens. In the case of electron capture, atomic number decreases by 1. This is what I meant to say, it actually decreases. No, it actually decreases. Whereas the mass is unchanged. An example of this, using calcium, if we were to shoot an electron at it, if we were to try to get it to capture an electron, in this case, the electron would be on the reactant side. All right, because we're capturing it, we're not releasing it. This atom is getting shot at with an electron, so it's getting added to it. The atomic number goes down by 1, but nothing happens to the mass. So identify this off the periodic table. We look at atom number 19, which of course is potassium, K. Now, in every single case we've seen so far, we've always had some particle to bookkeep to represent the energy. Here we have the electrons. This needs to have a number on top and a number on the bottom. Remember, we want these bookkeeping numbers to work out, to add up on both sides. So for example, $40 on the left, $40 on the right. That question mark, that's going to be a flat 0. Don't say the answer aloud, but think deeply as to what you think the bottom number will be. Remember, we need the numbers to add up, meaning we have 20 on this side right now. We need a number right here that adds up to 19. Hopefully, we all come up with the same answer, which is -1. Remember, technically speaking, this -1 is not exactly atomic number. We can never have a negative atomic number. But it helps us at least keep track of how the mass number and atomic numbers are changing. By using these types of equations, nuclear scientists can keep track of the various energy releases and chemistry that's going on, while also keeping track of the various electrons, beta particles, gamma particles, or helium particles. And those are the 4 types of radioactive decay, nuclear decay. You will not be given these descriptions as part of your exam, your final. You are expected to know them. And to understand a little bit more about how I might ask you a question, let's jump into the next problem set, the other handout I gave out. Problem set 7, nuclear chemistry. Again, this one will not have an assigned extra credit. The only extra credit for the final is that study guide. So this represents another worksheet for practice and additional help if needed. We're going to go through a couple problems together, and then I'll probably assign 1 or 2. Page 1, problem 1 says, provide all parent-daughter equations for the following prompts. Recognize that the words parent-daughter are used here just to describe the breakdown, the starting nuclei, the resultant nuclei. So this is no different than me saying reactant to products. But the key thing here is that it's asking for all of the equations. So let's go through what this process is going to look like. Hopefully by now, if you don't have a hard copy of your periodic table, you should have access to it either on your phone or a tablet, because we're going to have to refer to it. The first question says lead 211. Now, I did not give you the symbol, and technically speaking, 211 is not a feasible atomic number. I don't even think we go to 211. Looks like our highest atomic number is actually 103. So we, as of yet, at this moment, we don't know exactly what the atomic number is for lead. So guess what we have to do? We have to look on the periodic table. Now, you may be wondering, well, I have no idea where I'm going to start. I don't know what lead looks like. I don't know where it's going to be. But what we do know is the mass is around 211. So while it may not be exact, there's a chance this might be an isotope. It at least gives us a starting point. So just a quick scan on the periodic table. We're looking for a mass around 211. Okay, I'm getting close. I see mercury at 200. Keep going. Boom, boom, lead. And the fact that it's not exactly 211 shouldn't be a problem, because a different mass just means isotope. This is how we know beyond a reasonable doubt that we're dealing with lead that has atomic number 82. And we're told it has a mass of 211. Remember, the fact that the mass does not match is not a problem. It simply reflects that we're dealing with an isotope. First up, it undergoes a beta decay. So we would write the beta symbol. Hopefully we have our notes at the ready that describes what happens in beta. Let's just remind ourselves. In beta decay, the atomic number increases by 1. The mass is unchanged. So the atomic number goes up to 83. Nothing happens to the mass. Since the atomic number changes, the atom changes. So we have to identify atom number 83. Fortunately, the periodic table is in order. So number 83 is right after number 82. We see here that this is bismuth, Bi. That's not all, of course. Recall that beta decay does involve the formation of a beta particle. That is 0, -1. That's not all. The equation then says it's followed by an alpha decay. So another arrow. We're going to write the alpha symbol. Let's check our notes to be absolutely sure. In alpha decay, the atomic number goes down by 2, and then the mass goes down by 4. Make sure we have that right. Atomic number goes down by 2. That becomes 81. 83 minus 2 is 81. And then the mass goes down by 4. 211 minus 4 is 207. With a brand new atomic number, we have to identify. We check our periodic table. 81, as we see here, is thallium. That is TL. Alpha decay also results in the formation of a helium particle. Remember, this question did say provide all parent-daughter equations, so we need the full thing. And then finally, another beta decay. In the case of beta decay, nothing happens to the mass. The atomic number goes up by 1. Atomic number 82. We've already seen that. In fact, it was the very first one we dealt with. You could have remembered that, or you could have checked the periodic table. Conclusion is still the same. Atomic number 82 is lead. And don't forget that beta particle. This right here is the complete parent-daughter equation that shows all of the decays and equations of that lead 211. Not immediately relevant to the answer, but I just want to point something out. According to the periodic table, the mass of lead is 207. Of course, that's not what we started with. We started with an isotope, but recognized by the end, we formed a mass of 207. So this is an example of what I mean when I say that scientists can use these to manipulate radioactive isotopes, to make radioactive isotopes, or to break down radioactive isotopes. And by keeping track of these particles that are formed, we're able to explain any release of energy or any magnitude of energy that's released. Yes, Prab. Which part? It means that they are in succession, or they're successive. They are right after one another, meaning you had to do the beta decay first. That tells you that atom. Then the alpha decay occurs second. And then the beta decay occurs third again. So they are in order, meaning you would not have 3 reactions that all started with lead. Because the idea here is they are in order. They are after one another, successive. I would like to try one question from problem 2, because we see, looks like we're running out of time. At least get some practice as to how to approach this question. The prompt says, for each decay sequence below, determine the final daughter atom / nucleus, aka end product. So in this case, I am not looking for all of the equations. I just want to know what is the final one. What is the final atom formed? To give myself some space, I'm going to write it over here. All right, we have here the case of Neptunium-237. That means we first have to check the periodic table. Kind of scan for masses. We're looking for around 237. Okay, I see Rutherfordium as 265. Okay, that's a little ahead. Okay, radium is 226. That means I got to look at the actinides, the greens. And as I continue scrolling the list, I happen upon Neptunium. So the truth is that you genuinely just have to scour the periodic table for the element in question. A lot of these will repeat, so you'll get to know where they are as you do more practice, but you do have to scour. Neptunium is number 93. And we're told it has the mass of 237. All right. Now, there are two ways to approach this question, both of which involve basically the same level of math, just a matter of how comfortable you are with the math. Recognize that all I'm asking you for here is the final daughter. So I would not look for those individual particles that are formed. I don't care what's formed in the middle. I just want to know what happens at the end. So I would do very first would be our alpha decay. In an alpha decay, the mass number goes down by 4. The atomic number goes down by 2. I am not going to stop to identify this because I'm still not at the end. I'm going to immediately just go to the next decay, another alpha. So keep track. We've done one alpha so far. Now we're doing the other alpha. Mass goes down by 4. Atomic number goes down by 2. I'm not going to spend time trying to identify it because I'm still not at the end. Last up, we have our beta decay. That is our final decay. In the case of beta decay, nothing happens to the mass, whereas the atomic number increases by 1. This is clearly my final product, so I will now spend the time identifying it. Atom number 90 is thorium, TH. And that's all it's asking for, so I don't need to necessarily make note of the beta particle or the alpha part, the helium particle. My answer in this table would just simply be 229.90 thorium. That's one way to approach this, this problem. It forces you to go piece by piece to identify each individual decay, forces you to take it one step at a time. The other way you could have done this, depending on your comfort level with the math, is you could have recognized, okay, well, these are the decays in that order. Mass goes down by 4, goes down by 2. -4, -2. 0, +1. And we simply add those numbers together. In other words, get out that calculator. 237 -4 -4, okay, 229. Bottom number, 93 -2 -2 +1, 90. Where the same conclusion is reached. Thorium. Do we have any questions on nuclear chemistry or any of the problems we've done so far together? Well, congratulations. With that, we have now ended all of our Chem 1A material. We'll call it for today. We have lab in about 20 minutes. If you have any questions or want to talk about anything regarding this topic, a worksheet, or maybe the presentations, come see me now. Otherwise, I'll see you all in about 20 minutes.